Hello, and welcome to the third question on this worksheet, minimum spanning trees, or as I like to call them, minimum spanning trees. Basically, what we're going to do is we're going to take this undirected graph right here, and we're going to run our two MST algorithms on them, Kruskal's and Prim's, and we're just gonna basically run them and see what happens, see if we can get an MST. So I'm assuming that you already know what an MST is at this point, right? An MST is just the minimum graph that you would need to connect all of the different edges at once. It's not the same thing as a shortest paths graph, right? Because you can have a graph who has shortest paths, but if you want to get to all nodes in one go, the actual tree to do that is smaller. So let's begin by looking at Prim's. So we will start with Prim's algorithm. We are going to fill out this table as we do Prim's. It's kind of a weird table, but I'll explain in a minute. So Prim's, before we get into the algorithm, relies primarily on the cut property, which you may have heard of. I'm just going to explain it here one more time because the cut property tends to be kind of confusing for students. So basically, the cut property is like the closest we really get to like a real proof in this class, which is why it's probably confusing to a lot of people. Basically, what the cut property says is that for any cut in a graph, the minimum edge that crosses that cut must be in the minimum spanning tree. Okay, so what does that mean? So first of all, what is a cut? A cut is just a partition of a graph into two sets, right? So all that means is for this graph, if I wanted to take a cut, I could take these three nodes and I could take these four nodes together. That would create a cut. I could take, these three nodes. I could take these four nodes. I would create a cut. If I wanted to get really crazy, I could, even draw something like this, where I take these four nodes, and then I take these three nodes. That's a cut. You might think, right, like if you looked at those four nodes I took, this one, this one, this one, this one, you might think that that's, there's no way to set it into two separate sets because they're in different parts. But look, I just drew it and it works fine, right? In other words, it's just two sets of vertices divided in a graph. Why is it called a cut when I was just putting them in sets? Well, because equivalently, instead of thinking of it as like, here's one set and here's another set, you could think of it as I'm splitting one line down here that kind of extends infinitely and puts these into two sets, right? That's equivalent. Anyways, so that's what a cut is. Okay. The next thing is we say, okay, for any cut in a graph, the minimum spanning or the minimum edge that crosses that cut must be in the minimum spanning tree. Okay, here's one way to think of that. So let's look at this cut again. So you see that we have four edges crossing this cut, this one of weight 3, weight 5, weight 6, and weight 8, right? Okay, so minimum spanning tree, it connects all the nodes, which means that there must be some way to get from this cut or to this cut, or from this side of the graph to this side of the graph, right? There has to be an edge between that crosses the cut at some point, right? Because otherwise the minimum spanning tree would not be spanning, right? It wouldn't connect every node. Okay, that means that one of these four edges must be in the minimum spanning tree, right? We also know that since it's a minimum spanning tree, it doesn't matter, if it's the node from A to D or from C to D, E to F, like it doesn't matter which two nodes from inside each set we use to span, because we know that A is connected to every other node in its set. We know that D is connected to every other node in its set if we kind of apply this recursively, right? In other words, it can be any of these four edges, right? There's no way for you to pick one of these four edges and then end up with an edge that connects the two sets but doesn't connect every element within the set, right? Because the sets connect to each other. Okay, and so we know that there has to be at least one edge across this. We know that it can be any one of these four edges, right, is going to make a valid edge. And the minimum spanning tree is, of course, by definition, minimum edge weight. So we know it has to be one of these edges. So it's going to be the shortest, basically, right? In this case, it's going to be this one. This edge of weight 3 is going to be in our MST. It's a bit of a spoiler for later when we actually run the algorithm. But we know because we're looking at this cut that this one's going to be the edge. And if you wanted, you could just take every cut of the graph and you could say, okay, well, let's look at, this cut. What is the minimum edge that crosses this cut? Well, actually, there's three of them. It's this one, and this one. These are all weight 3. So it's going to be one of these, right, is going to be the cut. Any one of them could be in the minimum spanning tree, basically. Also spoil the later part of the problem. But that's basically what the cut property is saying. Okay, so let's do prims now. So prims basically involves us starting at a given node. We're going to start at A and basically cutting that node out from the rest of the graph and successively adding things to that cut and taking advantage of this cut property every single time in order to build our MST iteratively. We're also going to fill out this table as we do prims. Basically what this does is it says, okay, if we start at A, what is the cost to get from A to any other node, right? So this first section is filled out to us. These columns are going to be progressing iteratively. So basically when we start the algorithm, right, when we start prims, we don't know anything about the rest of the graph, right? We haven't popped any nodes. We haven't made a cut yet, basically, right? You could think of it almost as if this graph is this graph is like its own thing and the cut is like everything outside of it. I don't know. We haven't started, we haven't cut anything yet, which means that we don't know any of the distances, which is why we say our initial distance is going to be 0 for A because we're going to start at A, so we can start that one out, and the rest are infinity, right? This is similar to Dijkstra's, where if we don't know what the distance is, let's just assume it's infinite. Okay, first thing we're going to do is we're going to pop A, and we're just going to choose to pop A at the start. That's trivial where we start. So we're going to pop A like that. We know that A is 0 away from A, and in fact, A is always going to be 0 away from A. That's not going to change for all of these. Okay, and so now we've made this cut, which I've drawn with this dotted line here, right? In other words, this is one set and this is another set, right? That's the cut. So we look at these edges and we say, okay, we know according to the cut property that the minimum of these edges is going to be in our MST. We see that the minimum edge is AB right here, right? So what we're going to do is we're going to add this edge AB into our MST. I'll highlight it red. And then what we're going to do is we are going to update our values in the set over here, right? We know that the cost to get from A to B is going to be 2. And we know that the cost to get from A to C is 3, because it's right here. And we know the cost to get from A to D is 3, because it's right here, right? And then the rest of the costs remain infinite because we don't have any more information about them. Okay, so that's what we've done. We've basically done our cut property. We figured out this one is in the MST. We updated our table here, and now we're going to make another cut. Now we're just going to proceed iteratively. Now we are going to cut not only A, but we're going to cut all of the nodes that are connected to A via the edges in our MST. In other words, our red edges, of which there's only one right now. So let's make another cut, right? We'll make it right here. It's the nodes A, B separated from the rest of the graph. And you see that there are 4 edges that cross this cut, right? This one, and this one, to D, C, and E. Okay, at this point, we can choose any of these edges. It's arbitrary. I believe that the problem tells you to break alphabetically, which means we're going to choose AC because that is before A, D, and BE. So we're going to take AC, and we're going to put it into our MST. And then we are going to update the rest of the graph. So these values have not changed, but now we know that we have found a path starting from C and going to E that is going to cost us that is going to cost us a total of 3. Why do we know that? Because that is basically the path from B to E, from here to here, right? Because we just popped node B, so we updated all of that stuff. Okay, and then the other 2 are still infinite because we didn't learn anything about them. And then we can continue on. Okay, so now we've decided that C is the next edge, so we're going to pop it, which means we're going to draw a new cut. Whoop, I just got rid of my, 1 second. We're going to have a new cut. What is that new cut going to be? That new cut is going to be this cut right here. It's a little bit weird, but you see that there are actually 5 edges in it. The minimum edge, of course, is going to be the edge that is taking us to E. So we're going to include that one into our MST. Right. And now we can fill out the rest of the table. Okay, so we just took an edge from C to E, and it only cost us 1. We also know that if we want to take an edge from, if we want to take an edge to the other nodes, so if we want to take an edge to B, it still costs us 2. There's no faster way to do it than here. If we want to take a node, an edge to C, it costs us 3. There's no faster way to do it. We want to take an edge to D. It also costs us 3 via A, no way to do it. And now we can add F, because F is going to take us 6 to get to from C. The other one is infinite because we still haven't found G yet. Okay, great, great, great. Next part of the algorithm. Now we're just going to keep running. We're going to pop E this time. Let's make our cut. Just like that. 4 edges crossing it. We see that AD, if you remember earlier, I said AD was definitely going to be in the MST because we did a cut and showed that it was. Here's that cut coming out now. AD is going to be the MST. Great, so let's color it. So now we can add in some distances, 2, 3, 3, 1, 6. Nothing has changed here because we didn't get any new information about G. Now we're going to pop D. Okay, so if we pop D, the cut is now just here because we've popped all of these 5 nodes over here and we only need to pop these 2 remaining ones. We see there's 2 edges. The minimum one is DF of distance 7. Okay, great. Now we can update the rest of our chart. 2, 3, 3, 1, 6, 9. We can finally put a 9 in here because we have now uncovered this F node, which allows us to get to G with a weight of 9. Oh, wait, I just did that wrong. We didn't do that yet. That's the next one. We'll do that next time, sorry. Anyways, we're going to make one more cut here where we pop F now that we've just added it. Then we make a cut here, this. It's only one node on the other side, so of course, this has to be in our MST. Now we can update the values. I made a mistake earlier. Basically, now we can finally put 9 in here. That's because we just uncovered this G. We just uncovered this path that can bring us to G. And now, basically, we would pop G. We're going to pop G, even though we can visually see that G is the final node. Your algorithm doesn't actually know that there isn't like a node over here, H or something, so it's still going to pop G and look around. But it's going to pop G. It's going to see that there's no new cut to make. So all of these basically stay the same, and then we're done with the algorithm. Okay, so this, highlighted in red, is the MST, and this is the table. I will say don't worry that much about the table. It's not that useful. I don't really know why it's in the problem. The important part is you can do the cut property. So let's do it again, but really, really quickly in terms of the cut property. Okay, so let's start at A. Take a cut property. We see that this one is the smallest one. Okay, that's great. So then we know that this one is in the tree. Great, we can do the cut property again. We make a slice right here. We can see that any of these length 3 edges are in the cut property. So let's take AC because we're breaking ties like that. Make a cut property again. Now we can see that this edge of length 1 is the smallest. Do this, cut property again. See AD is the smallest. Do it like that. Cut property again. See that DF is the smallest. Cut property one more time. See that FG is the smallest. That's how you do it really quickly if you didn't have the table. And that's the kind of process that I would recommend getting used to. Okay, sure. That's all great. Now, the next thing we're going to do is we're going to do it in terms of Kruskal's algorithm, which is a different algorithm, but is still going to give us an MST. Okay, how does Kruskal's algorithm work? It works in 2 main parts. The first part is basically that you sort all of the edges by their weight, and then you just pluck off edges and keep adding them into the MST so long as they do not create a cycle. If that's confusing, let's just do it out, and hopefully it's really easy to understand on paper. First thing here is we have to sort all of the edges by weight. So I'm just going to manually do that, just visually inspect it. So I first see that we have this edge, CE. I'm going to always put the smaller letter first as well, just for the sake of formatting. So CE is weight 1. Then I'm going to look, do we have any weight 2 edges? Yep. We have AB. Have any more? No. Any weight 3 edges? So we have we have AD is weight 3 edge, AC Oh, let me do this alphabetically also. AC and then AD. These are weight 3 edges, and then B, E. Okay, great. Do we have any weight 4 edges? We do. It's BC. I can't draw letters. Then we say, okay, any weight 5, yes, CD. Weight 6, yes, CF. Weight 7, DF. Weight 8, EF. And weight 9, yes, FG. Great. So we've taken out every edge from this graph, and we've basically just sorted it by weight. So now what we're going to do is we are just going to iterate through from smallest to biggest, and we're going to add in an edge so long as it doesn't create a cycle. So the first one is CE. So let's take that off. Let's add CE into our MST. Great. Does that create a cycle? No, because we've only connected 2 different nodes. You can't create a cycle with just doing that. Okay, AB. So let's put AB in. Great. Doesn't create a cycle. AC. Let's put it in. Here's AC. Great. No cycle. Notice we have a chain of 3 right now, 3 edges, but we don't have a cycle yet. AD. So if we put AD in, looking good. No cycles. BE. Okay, putting BE in creates a cycle, right? We create a cycle in this way. So we're not going to put BE in. We're just going to keep going. BC would be right here. That would create a cycle. CD, that would create a cycle. So we're not going to do it. CF, no cycle here. All good. DF would create a cycle. Don't want to do it. EF would create a cycle. Don't want to do it. And then FG does not create a cycle. So we end up with this. So this is how you do it in Kruskal's algorithm. Great. There are a couple final conceptual questions right at the bottom here. Oh, turns out I was supposed to run Kruskal's algorithm over here. I'm not going to worry about that. Basically saying, does Kruskal's algorithm find the minimum spanning tree, work on graphs with negative edge weights, and does prims? Yes, they both work even when you have negative edge weights. Why is that? It's because of the cut property. Remember, when we did the cut property, we said, okay, the minimum edge that spans this cut must be in the MST. If the edge is -5, and there's no edge smaller than that, then it's the minimum edge. So there's no problem there. It's not like Dijkstra's where negative edges will break it. That's the main thing that we're testing here. Then the next one, true or false, a graph with unique edge weights has a unique minimum spanning tree. And the answer is true. So if you remember, when we were doing the algorithm up here, the reason we can come up with multiple valid MSTs in this particular graph is because sometimes there's ambiguity, right? Oops. If you remember, when we were doing prims and we were making the second cut where we were doing this, there are 3 edges here that are weight 3. Any one of these could be valid for the MST, right? Because again, the cut property just says the minimum edge must be in the MST, right? And all of these are a minimum edge. So we could have picked any of these 3 and it would have worked out just fine. So that's an example of why you would get multiple MSTs due to having the same edge weight. Therefore, if the graph has all unique edge weights, you're never going to run into that situation where you cut something and then you have duplicates, because by definition, you won't have duplicates. So every MST is going to be unique in a graph with unique edge weights. Anyways, I hope that helps. See you in the next video.